So far we've been looking at limits where the function is well defined at the value that x is approaching, in this case 3. And then we can just figure out the limit by looking at the function value at that same point, right? But we do run into a problem with an expression like the one we're given here, right? This expression is not defined at x equals 3 because the denominator can't be 0, right? So we can't just plug the value 3 into this expression and determine the limit that we're being asked for. We have to be a little bit clever here and see if there's something we can do with this function. Right? Well, it turns out, and it shouldn't hopefully be too hard to see, that this does factor. Right? We could think about the numerator as being x minus 3 times x plus 3. Right? Divide that by x minus 3. And then we can see that these x minus 3's divide out. Right? And we get the limit of x plus 3 as x approaches 3. Now, there's no problem with this expression, x plus 3. Right? 3 plus 3 is in fact 6. So it appears that we can figure this limit out, even though the expression or function that we were being asked to find the limit of doesn't exist at the value for c that x is approaching. Okay? But is this legal? Can we prove that this always works? And why does it work? All right. Well, we do happen to have a nice theorem. And this theorem says that if two functions agree everywhere but one point, right? Oops. The function agrees everywhere but one point, right? So you have a function f and you have a function g that, except for some specific value c, are always the same, right? If g has a limit as x approaches c, then f must also have that same limit. So this is a quick sketch, a graph of this function, f of x equals x squared minus 9 over x minus 3. And normally when we see a rational function, we start thinking about graphs with vertical asymptotes and things like that. But in fact, this is actually just a graph with a line, with a hole in it, right? Because x is not equal to 3. Now, it turns out to be the exact same function. It simplifies, right, as we just showed, down to x plus 3. Except that f of x equals x plus 3 is in fact defined at 3. So since these two functions are exactly the same, we could actually call this the g of x in our theorem up here. Right? Since the limit as x approaches 3 of g of x exists, right, giving us 6, then we know that f of x's limit as x approaches 3 must also be 6. Even though f of 3 doesn't exist, g of 3 does, right? That doesn't really matter for our purposes. Similarly, if we look at these two functions, f of x equals sine of x over tangent of x, where x can't equal pi, and g of x, which is cosine of x, right? F of x is really sine of x over cosine, of x, right? Which is really sine of x times cosine x over sine of x, which is really cosine of x. So f of x does in fact simplify to g of x, right? They are going to be exactly the same everywhere, except for the fact that f of x doesn't exist at x equals pi. So if I wanted to take the limit as x approaches pi of sine of x over tangent of x, right? Since this function is not well defined at pi, then I have to simplify it, right? Which I just showed above, right? So I'm not going to repeat those steps here, is really cosine of x. And cosine of x is perfectly well defined at pi, right? And the cosine of pi is -1, okay? So if you're trying to find a limit where the function is not defined at the value, then your best option and your best bet is really to see if you could simplify that function. So as we start to look at more and more limits, we want to have a little bit of a strategy. And our first bet, our first hope really is that we can let x become 2, right? But we quickly see that the denominator is heading to 0. If we try to let these x's become 2 as well, you can see that the numerator is heading to 0, right? You'll have 8 minus 6, which is 2 minus 2, which is 0. And this idea of 0 over 0 is what we call an indeterminate form. Determinate form, right? We don't know what's going to happen. 0 over 0 is a contradiction of two rules we've had. We've always learned that 0 over anything is 0. Nothing can be divided by 0. But if we do divide by infinitely small things, we go off to infinity, and these two are now working against each other. So we have to kind of figure out by exploring what's going to happen. It's not clear and it's not obvious, but the 0 over 0 case is always going to be an indication that we're going to have to do some simplifying. Now, since we have polynomials again, we might as well just think about whether or not we can factor, right? And I know that if this is going to factor on the top, right, it's going to have a 2x and an x. If I put a 2 here and a 1 here, right, I'm going to get my 4x here and my 1x here, and I can make that 4x negative, right, and the 1x positive. So make this negative, make this positive. And then, in fact, that's going to be the factorization of that trinomial we have above. Now, hopefully you're reviewing factoring and you'll get better at factoring. This x minus 2, right, is causing a problem in the denominator. And we know from the last example that it's going to have to divide out with a similar factor in the numerator. So if you're really struggling with the factor, you can basically hope that there will be an x minus 2 in the numerator as well, and then maybe it wouldn't be so hard to factor from there. We can see again that these are going to divide out, and we have now found an equivalent function to the original function we were given. The original function is not defined at 2, this function is. So now I can take the limit of 2 of this function, 2x plus 1, and I can see that the limit of the original function must have been 5. Right? So 0 over 0, we don't know what's going to happen. We're going to have to simplify and see what we can get. But sometimes we're not just dealing with polynomials, right? If we take a look at this one and we try to let x become 1, right, we're going to get 1 plus 3, right, which is 4. Square root of 4 is 2. 2 minus 2 is 0. 1 minus 1 is 0. Right? We have our 0 over 0 case again, and we're going to have to figure out what we can do here. So we're going to have to try to simplify. This again is where the challenge in calculus is often the challenge of algebra, and we have to try to figure out how we can simplify this. Now we can't just factor, we can't just get too creative and start canceling x's inside radicals with x's outside radicals. So we have to kind of remember what we need to do and sort of think about what the problem is so that we can then try to fix it, right? The problem right now is this x minus 1, okay? Which means we're going to have to get this x out of its radical. And if you multiply the same radicand, what's inside the radical by itself, with a square root at least, then you'll just get what's inside, right? We have something in algebra we call the conjugate. Whenever you have a sum or difference, we know that if we make the opposite sum or difference and multiply them together, we'll get a difference of squares. Okay, a little side note, just since the beginning of the semester, right? If you do a minus b times a plus b, right? This is our special pattern, a squared minus b squared. You can do your whole distributive FOIL, and the middle two terms cancel out, and we get this difference of squares. That's basically what we constructed here, a minus b, a plus b, right? And that way, all we get are perfect squares. And that way, the square roots will go away. If we just tried x plus 3 square root minus 2 times square root of x plus 3 minus 2, we would have middle terms that still had radicals, and then we wouldn't have gotten anywhere. Okay, we're good. So when I multiply this out, right, my a squared x plus 3 square root x plus 3 square root is just going to be x plus 3. And then we're going to take 2 times 2, which is 4. Now on the bottom, right, it might seem like we should take this x minus 1 and we should FOIL out everything here in the bottom. But if you remember when we started this, right, we indicated that the x minus 1 here is really causing the problem of the 0 in the denominator. And if we start multiplying it through with the other denominator, then we're going to lose that x minus 1. So sometimes things look a little bit worse than they are, but we're really just copying things down. And it looks like it's gotten pretty bad and maybe a little bit out of hand. But hopefully we can see what's going to happen in the numerator here, right? Plus 3 minus 4. Right? That's just going to give us x minus 1. That x minus 1 on the top will take out the x minus 1 that we left in the bottom. Right? And now, once again, we have a limit of an expression that is well defined at 1. So we can now go back to our rule of letting the limit be the function value. Right? The square root of 3 is 1 plus 3 is 4. The square root of 4 is 2. 2 plus 2 is 4. Right? So we get the limit of a quarter, right, as x approaches 1 for this original function. Okay. The algebra can get a little bit messy. If we had a plus at the first numerator, right, then we would have to add a factor with, or multiply by a factor with the minus. The key is to make the difference of squares. Okay. So when you're going through your homework, you'll see a lot of polynomial examples, rational polynomial over polynomial. You'll see some examples that involve the conjugate. And then one of the other sort of common examples we'll do is we'll look at rational functions where we have a fraction within a fraction. And then we'll be looking at common denominators. So in this example, right, we don't want to get ahead of ourselves. We don't want to assume that we have to do simplifying work unless it actually does, meet the right criteria. Our first hope is always that we can just let x equal 4 and we'll get a nice value and then we can be done. Right? That's what happened up until this point. But these examples we've constructed here are going to be sort of the exceptions to the rule that require more work. 4 minus 4 is 0. Right? If you put a 4 in here, you get a half minus a half, which is also 0. Right? So once you see that 0 over 0 situation going, you're going to have to do some simplifying. Right? And again, we want to try to keep our eye on the prize here. It's this x minus 4 in the bottom that's going to be the issue. So we always want to keep that x minus 4 separated, right, factored out, so that eventually we can get that last step where it divides out. So the key really is to focus on the numerator. And anytime you add or subtract fractions, you need a common denominator. Now, if we just had the numerator, we would find the common denominator and we would create two fractions, both with the same denominator. Okay. But one of the nice things we can do is, just like when we had an equation with rationals, we could multiply by the denominator. Right? When you had an equation with denominators, you could multiply both sides of the equation with the denominator. We have a fraction here. We could multiply not top and bottom of the fraction by the common denominator. So the common denominator of these two is going to be 2x minus 2. If you want, right, you can just do times 2 over 2, and you can do times x minus 2 over x minus 2 here. Carry around that fraction, and then simplify the fact that you have a fraction within a fraction. But if you give it a chance, I think you might see that the other thing you could do is to take this entire fraction, right? And multiply top and bottom by the LCD, okay? Now, at first, you may not see why this works or understand intuitively what's going to happen, but once you see what happens, I think it might turn out to be a lot easier, right? If we distribute this 2x minus 2 to both terms, since we made this 2x minus 2 include both denominators, right, we're going to get just what's left over. So if I multiply 2x minus 2 times 1 over x minus 2s, the x minus 2s are going to divide out. Now, if you don't see that happening in your head, which you never really have to, then you can just write it out like this, and then you can divide these out. Okay, but that's where this 2 over here came from. Similarly, if I put the 2x minus 2 with my half, right, then the 2's divide out, and I get x minus 2. Okay, so I have the limit as x approaches 4 of 2 minus x minus 2, and then I have x minus 4 times 2 times x minus 2. So basically, by multiplying top and bottom by the LCD, you're sort of taking care of two problems at once. One, I have to subtract these rationals, and two, I don't want to have a fraction within a fraction. If you want to do them in 2 steps, that's perfectly fine. Running out of space a little bit here, so I'm going to sort of distribute my minus sign here. And, there's mistakes you can make. It might be tempting. You might be looking at these x minus 2s and want to divide them, but that's not a legal rule. You can't divide when things are being added or subtracted, so you have to write things as a multiply. When I combine like terms in the numerator, I'm going to see 4 minus x over x minus 4 times 2 times x minus 2. Maybe I should have moved the 2 out front, but I've already committed to leaving it there, so I'll just leave it there. Now, remember, we had the x minus 4 sort of focused on as the problem, and on the top, we almost have x minus 4. We have 4 minus x instead. If you reverse the subtraction, you're off by a negative sign, right? 6 minus 2 is 4, 2 minus 6 is negative 4. So there's a rule that if you divide a minus b over b minus a, you get negative 1. You could also factor out a negative 1 times x minus 4 if that makes it easier. And then you can see, right, that the x minus 4s divide out, and you get the limit as x approaches 4, negative 1 over 2 x minus 2. And then once you let x become 4, you get negative a quarter. Okay? So again, the issue here is with the algebra. You have common denominators. Well, you have rational. You're subtracting rationals, so you need a common denominator, and then you have to be able to clear what we call an improper fraction, or a fraction within a fraction. All right. So for now, you're going to focus on polynomials, radicals, and rationals, and how to deal with those 0 over 0 cases by simplifying. Right. Next thing we'll do is look at some of the trig identities, and one of them in particular that we use something called the squeeze theorem to resolve, because there's no algebraic simplification we can do with that. That'll be in the next one.